Hello everyone, my name is Kathan and today we'll be discussing the problem Subarray Divisibility from the sorting and searching problems of the CSES problem set. Let's begin. Let me read out the question for you. Given an array of n integers, our task is to count the number of subarrays where sum of values is divisible by n. So in the input you can see we are given an array, right? So first line will be integer n size of array and next line represents n integers a1, a2, so on till the n contents of the array. In the output you have to print one integer, the required number of subarrays. And what is the required number of subarrays? In an array, you find me the contiguous segments whose sum is divisible by n, right? So you just return me the count, you don't return me those subarrays, right? So the example here, you can see there's a 5 size array given and you have to output all the subarrays whose sum, all the subarrays whose sum is divisible by 5. So there is one subarray here, you can see 1, 2 and 7 whose sum is divisible by 5, 10, right? So the sum is 10 and there is no other subarray whose sum is divisible by 5, so simply output is 1. Right, so I guess the question is clear. Let's go on to the iPad and discuss a bit more on this. First things first, let's talk about constraints here. So n was as high as 10 in 10 power 5, right? So order of 10 power 5. So what does it say? If you try to do an order of n square solution, it's going to consume you 10 power 5 into 10 power 5, which is 10 power 10 operations. But this is higher than 10 power 8. If you don't know, you cannot do more than 10 power 8 operations in 1 second. So n square is out of the picture. Then what is n log n then? N log n is definitely less than 10 power 8, right? So you can do n log n, you can do n, so on and so forth. So with that, the constraints are clear, and I guess the individual values were somewhere 10 power 9 to minus 10 power 9. So they were belonging to the integer range, minus 10 power 9 to 10 power 9. Okay, so that's interesting. Like if you sometimes have to do large sums, please take care that you are not causing overflow. And what else? Let's take the example test case now and try to understand this question. N was 5, right, in the example test case. Now here the 5 elements were 3, 1, 2, 7, 4. Now what you have to do is you have to find all the subarrays whose sum is divisible by n, which is 5, right? Whose sum is divisible by 5. Now what are all the subarrays? Like here there is this one subarray whose sum is divisible by 5, right? Because here the sum is what, 10, and 10 mod 5 is 0. Okay, is there any other subarray? No, there is no other subarray. But for example, let's say this was 0, then there would have been one more subarray, right? So this subarray. So in this case, this is also some 10, right? So if this is the array that is given to you, you have to output 2. You don't have to return me those subarrays. You just tell me how many subarrays are there whose sum is divisible by n. Okay, so I guess the question is clear. Let's discuss how to approach this question. Now you can like straight away think the brute force here, right? So the brute force is not very difficult to think. What is the brute force, guys? You enumerate all the possible subarrays. And how many subarrays are there? How many subarrays are there? You tell me, right? So there are order of n square subarrays. How? Because all the subarrays starting with the first guy are n, starting with the second guy are n minus 1, starting with the third guy are n minus 2. So if you add all of them, it turns out to be a sum of n natural numbers, which is order of n square. So one way is to brute force all the possible subarrays and check which subarray sum is actually divisible, or you can say mod n is 0. But this is the order of n square approach, and this clearly doesn't work. Okay, so if brute force doesn't work, then what are we gonna do? So what we do is, like, I guess this is a recurring theme in subarray based question. We try to think what is the count, of subarrays ending at I, right? For all I belongs to 1 to n, right? And of course divisible by n, right? So if you are not able to think in a brute force manner, then we'll try to find the contributions of every possible index in optimal manner, right? So that's what we do. This is a recurring theme for subarray based question. So we'll try to see what is the count of subarrays ending at a given index, whose sum is divisible by n, right? So if I write it more concretely, with sum divisible by n, right? All right. So if you recall the previous question, like subarray sums 2. So I do want you to remember that question, or if you have not watched that video, at least you should know what is the optimal approach for that question, right? I'll link the video, like you link that video in the I button above. You can check that out. But if you recall the previous question, how did we approach the previous question? Like there you are finding how many subarrays ending at given index had sum x, right? Here we are finding how many subarrays ending at given index has sum mod n equals to 0. Okay, so the previous question, how did you find the contribution of I? So you were dealing with prefix sums, right? So what we effectively did is, whenever I am at current I, right, if I want to find the contribution of this I know that the prefix sum till this part is pi. Okay, now if I just subtract, if I subtract pi minus x from it, all that will remain is x, right? So the contribution of I, right, the contribution of I was count of all prefix sums, count of all prefix sums having sum y, which was nothing but pi minus x, right? So if you want to find the contribution of a given index for our answer in an optimal way, what we did is we find out all the possible prefix sums. So whenever I'm at I, I'm gonna find out all the possible prefix sums here, which yields a sum pi minus x. Why? Because all of these contribute to my answer, right? Because for all of these prefix sums, I can get a subarray with some x. This I guess you already know. Okay, let's try to extend this idea for this current question then. Alright, can we extend the same idea in this question in some way? Let's try to see. So in this question also we want to find the contribution of I in an optimal manner. Now let's call this, you can say, prefix sum pi. Now what do you know about pi? Let's call this pi mod n r. So in other words, pi can be written as n into some k plus r. This r is a remainder when you basically do pi mod n, right? This r is a remainder, right? So this r belongs to 0 to n minus 1, right? It belongs to 0 to n minus 1. Okay, so let's say pi can be written like this. Cool. Now if you can find some pj here very attentively, if you can find some pj here, which can be written like nk dash plus r, that is leaving the same remainder. What is this part, guys? You subtract from pi pj. So what does it become? It becomes r gets cancelled out. So if you do pi minus pj, so I'm talking about this part, guys. What is this part? This part is pi minus pj, right? So pi minus pj will become r gets subtracted, and then you have n common k minus k dash. What do you know about this, guys? What is this value? What is this value? Like, what is this value turned out to be? A multiple of n. That is, the sum here mod n will be 0. The proof is right in front of you. If you know that pi yields a remainder of r, and you find a pj before it, which also leaves a remainder of r, this portion, like, you have got a subarray whose sum is divisible by n. That is to find contribution of I. Let me just show this to you also. To find contribution of I, okay, count all pj's. So this j is less than I, right? So you want to find all the prefix sums before it such that pj mod n is same as pi mod n, right? The remainder, you find all the prefix sums before this guy whose remainder is same as the remainder left by current prefix sum. For all of those prefix sums, you get a subarray divisible by n. Let me show you an example. So let's take an example here. Let's take the same example, 3 1 7 3 1 2 7, and we took it 0, right? So n is 5 here, right? Now what is prefix sum till this part? Prefix sum till this part is, if you want to see pi, This pi is 7 plus 2, so on and so forth. So this is turning out to be 13, right? So what is the remainder here, guys? 13 mod 5. 13 mod 5 is 3. Okay. Now, can you find a perfect sum before this I? Can you find a perfect sum before this I which also leaves the same remainder? Because if you can find it, you subtract that part and whatever the left part is contributes to your answer. It will be a subarray with whose sum is divisible by n. And indeed, you have a perfect sum here. Indeed, you have a perfect sum here. This pj with a 3, and this 3 mod 5 is also 3 mod 5 is also 3. So this contributes to the answer. Makes sense? Similarly, like the same logic holds true here. So if you come here, the perfect sum is again 13. You find me a perfect sum before it which yields a remainder of 3, and you'll be able to find it. Which one? The same one. Right, so here this is how the answer gets calculated. So all we need to do is keep track of remainders of perfect sums, right? So if I try to draw the parallel with the previous question, in the previous question we were keeping track of sum and the respective counts or frequencies, right? So how many times this perfect sum has occurred till now. But in this question, instead of keeping track of the sum's frequencies, we mod this sum with n and we keep track of the remainder of this perfect sum. Right, so how many times a perfect sum has occurred with a given remainder. In other words, keep track of remainders. Now, you know that whenever you mod a guy with n, it yields a remainder in range 0 to n. So all the unique keys, or you can say all the unique remainders possible in this map are order of n. So this says that the map size won't grow beyond order of n, which is important. Why? Because n is as high as 10 power 5, and map is as high as 10 power 5, and you cannot have very, you can say, large size maps. If n was very general value, let's say some 10 power 9 or 10 power 18, like if you don't know, a local variable size cannot be more than 10 power 5, right? And a global variable size cannot be more than 10 power 7. This is very interestingly given that you have to find all the subarrays divisible by n, and n was less than 10 power 5. So that is, you can actually maintain a map with all the unique remainders. So that's one interesting thing. Fine. So I guess you can directly write the pseudocode for this. This is exactly similar to the previous question. But what I want to discuss here is the interesting thing about remainders and the mod operator. So what happens is, like, you may be scratching your head that the mod operator can also return negative remainders, right? So you can say, deliberately deferred this discussion till now because I wanted to explain the concept first. Now this mod operator works a bit differently in case of languages like Python and C++. In case of Python, whenever you have this mod operator, it always returns positive reminders. Okay, so in case of Python, I don't think this approach should create any problem for you. This would work straight away. But in case of C++, there is a little bit nuance that you have to take care, right? So let's see, like, what is the nuance I'm talking about. For Python guys, I guess you can go ahead and very well implement the solution and it will work. But for C++ guys, please stay for a bit. I'll show you what I'm talking about. Let's say n is 4. And you have values like -4, -3, -1, -3. Let me just take all the values from -4 to 4. -2, -1, 0, 1, 2, 3, 4. Now, I want to perform a mod with n for all of these values. Now, these two values are clearly 0, right? So, -4 mod 4 and 4 mod 4 is 0. Okay. And these values also, you know, that 1 mod 4 will be 1, 2 mod 4 will be 2, 3 mod 4 will be 3, right? Similarly, if you take 5, 6, 7, so on and so forth, so this again will follow, right? So 5 mod 4 will be 1, 6 mod 4 will be 2, 7 mod 4 will be 3, and 8 mod 4 will be 0. So this is fine. Now, what will be the answer here? Like, what do you expect? Like, at least this will be 0, so this is obvious. What do you expect here? What should be the answer here? Like, see, ideally you want that all the remainders should lie in range 0 to n minus 1, right? So that's your general notion. You want the remainders, you can say my number, let's say my number to be represented as n into k plus r, where this r lies in range 0 to n minus 1. You want this r to be positive. But the problem with C++ is it here leaves a remainder of -3. It leaves a remainder of -2. It leaves a remainder of -1. So why it does like this? It is actually calculating this -3 like this. It is showing that it is equal to 4 into 0 plus minus 3. It is representing this minus 2 like 4 into 0 plus minus 2, so on, right? So this is the fundamental problem with how C++ calculates the remainder. So C++ returns this remainder, right? But what do we want? Let's take a step back and try to understand how remainders are formed. So let's say n is still 4, but we have 13. So you know that 13 mod 4 is 1. But how does that come? It is 12 plus 1, right? So this 12 is nothing but 4 into 3. Okay. So similarly, you know that 18 mod 4 is 2, right? So, but how does that work? Like you represent 18 like this, 16 plus 2, which is 4 into 4 plus 2. In other words, in the number line, you have 13 here. So you first try to reach 12, and whatever you try to reach 12, and whatever remains is the remainder, right? And the same ground, you try to reach 18. You first reach 16, the closest remainder, you can say the closest multiple of 4 from the left, and whatever remains is the remainder. So if this is the logic you do when you calculate the remainders, the same thing should happen for negative numbers as well, right? To maintain consistency. So if you want to find the remainder when minus 3 mods with 4, you find the closest multiple of 4 from its left. What is the closest multiple of 4 from its left for minus 3? It's minus 4. So the remainder should be, if you write it, so how is minus 3 formed? The closest multiple of 4 from left, which is minus 4. So it will be 4 into minus 1 plus 1. So here the remainder should be 1. Simple. Similarly for minus 2, what is the closest multiple of 4 from the left? It is minus 4. So again, 4 into minus 1. You try to reach as close as possible. Plus 2. Simple. For minus 1, what is the closest multiple from left? So ये पूरी रामायण में इसलिए कर रहा हूँ because I want the R to be positive. That is, the line range 0 to n minus 1, right? So here it will be what? 4 into minus 1 plus 3. So this strategy always ensures that you have a remainder which comes in range 0 to n minus 1. And there is no PhD. This works. I'll show you why. Let's say we have n equals to 4 and these are the values. So pi here, let's say prefix sums like p of 2 is here 5, right? You know that 5 mod 4 will be 1. Now is there a prefix sum here which yields remainder 1? Indeed. So this thing, like this pj equals to 3, pj equals to minus 3 mod 4 yields the remainder 1, we just saw. So if you do pi minus pj, which turns out to be 5 minus 3, it gives a sum 8, which is indeed a multiple of 4, right? So, but how do we convert this? You can say this C++ is always going to return this negative value, right? So how do you do this? How do you convert it to the positive counterpart? It's actually much simpler than you think, and you have actually seen this trick a lot of times being used. Maybe you didn't know the reason for that, so I'll show you. If let's say R does belong to 0 to n minus 1, okay, then there is no problem. But if R is negative, what you can do is to get the positive counterpart, what you can do is to R you can add n and take mod again. Okay, so if I show you, so for minus 3, if you add 4 and take mod again, it's gonna return what? 1 mod 4 is indeed 1. Okay, similarly for minus 2, you add 4 and take mod again, it's gonna return 2 mod 4. Okay, and similarly 2, and for minus 1 also, you add 4 to it and take mod again, so it's gonna return 3 mod 4, which is 3. Now this is what you have to do effectively, right? So if the remainder is negative, you have to add n to it and take mod of it. If you observe a bit closely and remember the properties of mod, if R is positive, it's not gonna change its value. See, if R is 2 and you add 4 to it and take mod of it, it still is gonna return 2, because the property of mod, right? A plus b mod m is a mod m plus b mod m, right? So this is how it works. So this formula works because of the property of a plus b mod, right? So if you observe, this is why this strategy works. Anyway, so with that thing cleared, I guess the question is done and dusted now. We now know the remainder should be calculated using this formula. So what is this formula? You first find R, like how would you do naturally? So whatever prefix sum you had, let's call it pi mod n. But you know that this can become negative. So what you do is you add n to it and take mod of it. right? So if r was positive, the value is not going to change, but if it was negative, it's going to convert it to the positive counterpart, right? So yeah, I mean that ends our discussion on the question. So you can code it up in the same manner that we did in the previous question. Nothing changes. We initialize our map with the initial frequency of r equals to 0 being 1, right? Because when you start a journey, there is, you can say, a imaginary prefix sum whose remainder is 0, right? Because the first value itself can be divisible by n. So that's why. And that's wrap up our explanation. If you did understood the explanation, please comment understood in the comment section of the video. And let's look at the code and wrap up this video. Alright guys, so here's the code. So first things first, I'm taking the input. Notice I'm taking here everything as long. The simple reason being it can cause overflow or underflow, right? Because all the array values are lying in range minus 10 power 9 to 10 power 9, and the n can be as high as 10 power 5. So 10 power 5 into 10 power 9, if it happens in integer, it will be 10 power 14 overflow, or minus 10 power 9 to 10 power 5, it's going to be minus 10 power 14 underflow, right? Okay, so I have a map here. I'll name it psums, but what it stores is, it actually stores the remainder of a prefix sum and its count, right? So initially we have an imaginary prefix sum whose remainder is 0, right? And yeah, so cur sum keeps track of the current prefix sum. Total is keeping track of our answer, right? So we are gonna take the contribution for every possible I, if you didn't forget. Okay, so we go from I equals 0 till n, we find the current prefix sum, we find the remainder. So how do we find the remainder? Current sum mod n plus n mod n. This ensures that r always lies in the range 0 to n minus 1. So all the prefix sum with the remainder mod contributes to the answer, right? We just saw. So we're just gonna add, find all the prefix sum which leaves the same remainder as the current guy. So add the contribution for all those prefix sums, and we increment the contribution of a remainder, right? We increment p sum of mod, right? So we increment the count of a current remainder. Fine. And afterwards, like if in this loop ends, we have taken the contribution for every possible I and we increment the total. What is the time complexity here, guys? See, we are running this loop once, right? So all of this is input and fine. This loop is run like once, which is order of n, and in each iteration, what we do is we take values out of the map, we increment the values in the map. So it is nothing but map operations. So these map operations are log n, right? So the time complexity turns out to be n log n. Space complexity relies on the what is the maximum size of map. We already know that the remainders, unique remainders, are in range 0 to n minus 1. The space complexity will be order of n for this, where we may have to store all the possible remainders from 0 to n minus 1 with this order of n. So space complexity is order of n. So yeah, I mean that's about the code. I hope you got something out of this video, especially the mod part. And if you did find this video helpful, please give it a thumbs up, and I'll see you in the next one.